Okay, hi guys. Hopefully you've copied out the note on the mole already, and I'm going to walk you through it right now. So I am going to jot some notes down the same that you just saw, but this way I can stop and actually explain things as we go. So you've already completed the discussion on what is measurement anyways. And we've seen that there are a variety of measurements that actually are very arbitrary and don't mean the precise values that we think they do. Like maybe you looked up the foot and found that it's not defined as 12 inches, but its original measurement was actually the length of King Charlemagne's foot back in the 1300s. So as we talk about the mole, we just need to keep in mind this is a defined quantity of measurement, much like a dozen or a gross or a pound. And we're just going to package up these massive numbers we've been dealing with in terms of particle size or particle numbers and go on from there. So to start with our precise definition of the mole, I'm going to focus this here. And just bear with me, this is the very first video I've done, so hopefully it works out. Okay, a mole is defined as the base unit used to measure the amount of a substance. So something to note, what is 1 mole? 1 mole is the number of particles. In this case, the type of particles we're going to be talking about is the atom, so the number of atoms, in 12 grams of carbon. So what is this actual number? Well, in 12 grams of carbon, there are 6.022141179 times 10 to the power of 23 atoms. So you can see right here why we are packaging up into a mole instead of the number of atoms. This, should I write it out for you? Sure. So if I started, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 20, 21, 22, 23. It's that many atoms. We have the option of writing it out like this, writing out like this number of atoms, or saying 1 mole. Me, I will take 1 mole. Thank you very much. So this number here is actually defined as Avogadro's number, and we're going to be using this a lot, so please get very familiar with this value. And we actually round it down. I don't make you go to 8 decimal places. Instead, we just go to 6.02 times 10 to the 23. So this is the number of atoms in a mole. It also represents the number of molecules if we're looking at a molecular compound in a mole, or the number of what we call formula units in a mole. We'll talk about formula units right now because we need to look at how we break down particle units. So particle units, if we have 1 particle of an element, we can have 1 particle of a molecular compound, and we can have 1 particle of an ionic compound. If you haven't already filled this in, I want you to pause this video and fill in what you think these terms are. 3, 2, 1, pause. And we're back. So I really hope that you knew the name for 1 particle of an element is an atom. 1 particle of a molecular compound is a molecule. Maybe you're seeing a trend up here. Now, our last one particle of an ionic compound, this one we haven't really referenced before. We don't call it a molecule because it is not formed using a molecular bond. We call it a formula unit instead. Now, how do we calculate the number of moles versus the number of atoms versus Avogadro's number? Okay, Avogadro's number, I'm just going to jot back up here, is noted with a capital N subscript A. So our formula, N equals uppercase N over uppercase NA. And I can hear you all right now. Why are there 3 different N's in the same equation? Guys, these are the times we live in. We just have to deal with this. So N equals uppercase N over uppercase N subscript A. What do each of these in our magical equation here represent? N is the number of moles, and the unit we use is the mole. Uppercase N is the number of particles. So this may be atoms, molecules, or formula units. And yes, you do need to write these out the whole time. We don't have a short form for them. And A is, as we mentioned above, Avogadro's number, which is always represented by 6.02 times 10 to the 23. Now your unit here is going to be something per mole. So it may be atoms per mole, it may be molecules per mole, or it may be formula units per mole. Let's try this out. My first example, for example, how many molecules are in 2.5 moles of water? Let's take a minute and note what we've actually got here. We're being asked for molecules. That's our particle unit. That is uppercase N. We are given our number of moles. That's lowercase n. And remember that Avogadro's number is a constant. Okay? It's always the same. So it's always 6.02 times 10 to the 23. The unit in this case will be molecules per mole. I have N equals 2.5 moles. Do you need to write this out? Yes, you do, guys. We're showing full solutions here. Our assessments are going to be tricky on online learning. There's going to be a lot of multiple choice, but I will at times have you upload your full solutions to me to take a look. That may just be you take a picture and upload it, not suffer through trying to make exponents in D2L. So let's solve this. We know that our formula is N equals uppercase N over NA. I'm going to rearrange this now to isolate N. So I'd have uppercase N equals lowercase n times Avogadro's number. And here I can sub in. So that's 2.5 moles times 6.02 times 10 to the 23 molecules per mole, which gives me 1.505 times 10 to the power of 24 molecules. And I know it's been several weeks since I've seen you guys, and even longer since we talked about it, but we need to think about sig digs. We're looking at multiplication, so I look for the lowest number of sig digs. I have 2. Here I have 3. So that means my final answer will have 2 sig digs. I'm going to round that to 1.5 times 10 to the power of 24. My scientific notation doesn't count as significant number of molecules. And there's our first example. Let's try the next one. How many moles of sugar are made up by 6.734 times 10 to the power of 22 molecules? Probably a question that you've come across in your everyday life in the last 3 weeks of shutdown, right? I thought so. So let's identify what we know. We're being asked for moles. That's lowercase n. We are given the number of molecules. That's our uppercase N. And don't forget, Avogadro's number is a constant. We already know it. In this case, we just have to parse out what is the unit. We're dealing with molecules, so it is molecules per mole. Okay, I can keep with my original form of the equation here at lowercase n equals uppercase N over Avogadro's number. And I'm just going to sub in. Divide that number of molecules by Avogadro's number. Please note that, yes, I am putting my units in every step. If you had physics, I know sometimes they don't really require it there. I do want units carried through all the steps because we're going to have to start removing some. So what does this give us? It gives us 0.118604665 moles. That's a lot of significant digits. If I look here, though, I have 1, 2, 3. This may be a constant, but if we refer back to our original value, it's already been rounded down. So I can't count that as an absolute value. All right, it does count as significant. So that's 3 sig digs, which means I need to round my final answer to 3 sig digs, which gives me 0.119. I'm rounding up moles. Okay, we're going to do one more sample problem here. This is taking us to the next level. So I've asked how many atoms of carbon are in one tablet of aspirin. I've given you the molecular formula here. If one tablet contains 3.22 times 10 to the negative 2 moles of aspirin, there's our lowercase n. Now, I don't just want to know how many molecules this contains. We're going to go from the number of moles to the number of molecules, from the number of molecules to the number of atoms. This is now going to take 2 steps. Let's go. I know that N is 3.22 times 10 to the negative 2 moles. I know Avogadro's number. That's molecules still because we're looking at our molecular compound. But I don't know the number of molecules present in one tablet. So N equals uppercase N over NA. Well, I'm going to rearrange. Uppercase N equals N times NA. That gives us 3.022 times 10 to the negative 2 moles times 6.02 times 10 to the 23. I'm getting tight in here. Molecules per mole, which when I round for significant digits gives me 1.94 times 10 to the 22 molecules. Now this is the number of molecules of aspirin, okay? So from there we need to recognize that in our molecular formula, so 1.94 times 10 to the power of 22 molecules of C9H8O4. And the question asked us for the number of atoms of carbon. So we need to recognize in one molecule, how many atoms of carbon are there? There are 9. So we're going to take this number, 1.94 times 10 to the 22 molecules, times 9 atoms per molecule. That is going to cancel out our molecule unit, which gives us a final answer of 1.75, keeping the number of sig digs. This is a counting term. It doesn't count as significant. It's not been rounded. Atoms of carbon. And there is our final answer for this final example. If you have any questions, we're going to talk about how to get in touch with me on that. There will be a Google Doc as well as a daily Zoom conference that you can drop into. It's optional. I'm also going to post some more resources for you guys to look through. You may or may not find it helpful. It's going to depend on your learning style, but I will have, it's going to be called a quiz, but it's more just a check-in or I'm going to do it as a discussion to see what you guys are getting for your homework. So I look forward to talking to you later. Bye-bye.